Hello friends, I am Dhara Pomal. I will discuss SR flip-flop of Unit 3 of Digital Fundamentals subject. I will cover the points like SR flip-flop, the clocked SR flip-flop and as applications of the flip-flop. So first of all, we will see what is the flip-flop and the difference between latch and flip-flop. Flip-flop is 1-bit data storage element. At a time, it will store 1-bit data. Nowadays, we are using these flip-flops in our daily life in the applications like computers, mobiles, laptops, right? So you are using memory in all these devices. So in the memory, we are using this flip. Now we will see the difference between latch and flip-flop. The latch is level triggered, means outputs can change as soon as the input changes. It is a transparent device. And flip-flop is age-triggered device, means only changes the state when control signal goes from high to low or low to high level, as we have already discussed in the previous lecture. The flip-flop is age-triggered device and the latch is level-triggered device. Fine. Now we'll see the one of the type of the flip-flop, that is SR flip-flop. As its name suggests, SR indicates set, reset. We can also pronounce as RS flip-flop. The SR flip-flop has 2 inputs, 2 outputs. 2 inputs are S and R and 2 outputs are Q and Q dash. So Q and Q dash are both are complement to each other. So it has 2 stable state, we can say like this way also. Such flip-flop can made simply by cross-coupling to inverting gates. Either NAND or NOR gate could be used. Now we will see the figure, the detail of NAND gate SR and NOR gate SR flip-flop, or you can say RS flip-flop. The figure A shows RS flip-flop using NAND gate. You can see here there are 2 NAND gates. Output of one gate, say A NAND gate, we are applying to one of the input of logic gate, that is NAND gate, to B. And output of this logic NAND gate, that is B, we are applying back to the one of the input of NAND A gate. So we are applying set and reset inputs. These are the outputs Q and Q dash. Both the outputs are complement to each other. Now this figure B shows the RS flip-flop using NOR gate. Here the function will be similar, means the connections will be similar, means the output of NOR gate A we are applying to the one of the input of NOR gate B, and the output of NOR gate B we are applying one of the input of NOR gate A. Again 2 inputs are there and 2 outputs are there, Q and Q dash. This is the symbol of the RS flip-flop. Set, reset inputs, Q, Q dash outputs. Fine. Now we will see the working of the circuits in detail. First of all, we'll see RS flip-flop using NOR gate. As you know, the truth table of the NOR gate, logic gate, I will draw here the truth table of the NOR gate for your reference. Now we will take all these combinations and we'll see the function of this circuit. First combination, say 0, 0. So there is no dominating input. Output is 1. This is the first case. I am talking about first case. Whenever R and S both are 0, then output the output of the flip-flop will not change. Why? Because there is no dominating input. We will get previous state at the output terminal, means there is no change in the state of Q and Q dash. So whenever we'll apply 0, 0, the output of the RS flip-flop will be stable, means we will get the previous output as it is. Fine. In the next case, that is R is equal to 0 and S is equal to 1. Here R is equal to 0. Here we are applying R is equal to 0. So here, second case, R is equal to 0, S is equal to 1. As per the definition of the NOR gate, if any one of the input is 1, output will be 0. So here in the B gate, means lower gate, NOR gate, I am applying S is equal to 1. So one of the input is 1. This Q dash will be 0. Now this 0 we are applying to NOR gate A. This is one of the input. Q dash is one of the input of logic A gate. So here two inputs are there, 0 and R is also 0. You can see here 0, 0 means at the output terminal we are getting 1. So here we will get 1. Means Q is equal to what? 1. Fine. So we can say in another words, when S is equal to 1, Q will be 1 and Q dash will be 0. This is nothing but the set mode. We can say flip-flop is in the set mode because whenever set input is 1, Q output will be 1. This is what? Set mode. Next case, that is R is equal to 1, S is equal to 0. In this case, the reverse case of this condition of the previous case, here we are taking 1 and this input 0. So as you know, if any one of the input is 1, output will be 0. So here in the third case, we are getting 0. So instead of 1, now we are getting 0. This 0 we are applying to one of the input of this NOR gate B. So here 0, 0, 0 we are applying to this NOR gate. So Q dash is equal to 1 because both inputs are 0, output will be 1. Fine. So whenever R is equal to 1, so whenever R is equal to 1, Q will be 0, means the circuit will be in reset mode. Fine. And whenever we'll apply fourth case, means R is equal to 1, S is equal to 1, at that time circuit becomes in the raise condition. Practically, this case we cannot apply. This is the disadvantage of this RS flip-flop. So both inputs are 1, means you know that Q and Q dash will be 0, 0. So these are the complement to each other. So this case cannot be possible because we are getting Q and Q dash, both output are 0. So this case is not possible. In this case, it will raise the condition. It will raise the flip-flop circuit. Fine. So this is what? Indeterminate mode. We can say indeterminate. So there are 4 cases as we have discussed. I have taken here in the tabular form. So in the 0, 0, as I told you, there is no change at the output terminal. In 0, 1 means when S is 0, Q will be reset, and when S is 1, Q will be set, means the circuit will be in set. mode. Fine. So there are 4 cases in this SR flip-flop. Fine. Now we will see SR flip-flop using NAND gate. This is the circuit of SR flip-flop using NAND gate. You can see here we are applying S input to NAND A gate and R input to NAND B gate. Output of this NAND gate, we are applying one of the input to NAND gate B. And output of NAND gate B, we are applying one of the input to NAND gate A. Again, we are getting 2 outputs, Q and Q dash, both are complement to each other. Now you know the truth table of the NAND gate, that is 1, 1, 1, 0. Means if both the inputs are 1, output will be 0. And if one of the input is 0, output will be 1. Okay, I will write the truth table for your reference. One of the input is 0, output will be 1. Both inputs are 1, output will be 0. Fine, now we'll take all these 4 cases in detail and we'll see the function of the circuit. In case 1, R is equal to 1, S is equal to 1. I am taking the last case, that is both inputs are 1. So the output remains in previous state. Why? Because you know that whenever both inputs are 1, there is no change in the output. Means the circuit will hold the data. Now the case 2, R is equal to 1, S is equal to 0. Fine. Whenever one of the input is 0, output will be 1. Here I am applying S is equal to 0. So output of this flip-flop will be 1. Here we are applying S is equal to 0 and R is equal to 1. So this output will be 1 according to this truth table. Now this 1 we are applying to one of the input of NAND gate B. Now here to this NAND gate B, we are applying 1, 1. So 1, 1 means output will be, this Q dash will be 0. Fine. So Q will be 1, Q dash will be 0. You can see here, we are getting complement output. Okay. In the third case, R is equal to 0, S is equal to 1. The reverse condition of this means here, now we are applying the third case, that is I am writing here 0 and S is equal to 1. So here one of the input is 0, output will be 1. And this 1 we are applying back to this gate, logic gate A. So 1, 1 gives output 0. Okay. And both inputs are 0. This is again race condition. This practically this case cannot be possible, because you know that whenever one of the input is 0, we are applying S and R is equal to 0. So we are getting Q and Q dash equal to 0. So this condition cannot be possible. Practically this condition cannot be possible for this NAND gate. It is the reverse of the NOR gate. In NOR gate, whenever we are applying R and S is equal to 1, that condition is not possible. Here R is equal to 0 and S is equal to 0. This condition cannot apply to this NAND gate circuit. So I have taken all these 4 cases in tabular form. You can see here the truth table of this flip-flop. 0, 0 means indeterminate state. 0, 1 means Q will be 0, means flip-flop in reset mode. Whenever S is equal to 1, Q will be 1, means flip-flop will be in set mode. And 1, 1 means there is no change in the output, means we will get previous output as it is in this case. Okay, so this is what the circuit using NAND gate. Now we'll see the clocked SR flip-flop. You can see here in this figure, this is nothing but the SR flip-flop using NAND gate. But we have connected two extra NAND gate to this inputs of the logic gates. The clock circuit of SR flip-flop NAND gates is shown in this figure. This circuit is formed by adding two NAND gates to NAND-based SR flip-flop. You can see here, this is SR flip-flop and we are using two NAND gates here. The inputs are active high as the extra NAND gate inverts the inputs. A clock pulse is given as input to both the extra NAND gates. Here you can see the clock input is common to both the NAND gate, extra NAND gates. We are applying clock inputs, that's why name is clock SR flip-flop. The function will be similar as we have seen in the previous NAND gate circuit, but the simple change is we are adding two NAND gates here. Okay, so whenever here I have taken the positive edge trigger clock SR flip-flop. Means what? As we have discussed in the previous lecture, positive edge trigger means the circuit will change its state at positive trigger. Okay, so whenever clock input, clock will change its states from negative level to positive, means low level to high level, output will change, output will trigger the state. So whenever here, you can see here, this is a clock input. Whenever clock pulse is this down arrow indicates negative edge trigger and the upper arrow indicates positive edge trigger. So whenever we'll apply negative trigger or 0 or 1 means level trigger, level clock pulse. So level trigger clock pulse. So at this combinations, there is no change in the output. Why? Because of this clock input. Whenever we will use positive edge trigger clock pulse, then only output will trigger the state. Otherwise, it will not trigger the state. We will get previous output as it is. This circuit shows the NOR gate SR flip-flop with this portion shows the NOR gate SR flip-flop, but we are using this extra logic gates and gates here, and again we are applying clock pulse. So there are so many possible combinations, or we can say we can design the circuit of this clock SR flip-flop by using NAND, by using NOR. Here we are using AND gate. The previous one we are using extra NAND gates. So there are so many possible circuits you can design. Now this is, we will see the function of this circuit. I have taken the truth table here. You can see in this truth table, there are three inputs, means this clock input, R input and S input. Okay, so clock, first case, this arrow indicates negative edge trigger and this arrow, upper arrow indicates the positive trigger. Okay, so whenever this arrow is at downside, means this is this indicates we are using negative edge clock pulse, and upper side arrow, this arrow indicates we are using positive edge trigger clock pulse. So here in this circuit we are using positive edge trigger clock pulse. So whenever negative edge clock pulse or either 0 or 1, at this cases, if R is equal to and R and S is equal to 0 or 1, there is no change in the output state. Now here this indicates positive edge triggering clock pulse. So now first case, suppose 0 0, so we'll get last state. This table you can see, as we have seen in the NOR gate SR flip-flop, this table will be same. Okay, Okay, so this table is similar as we have discussed the RS flip-flop using NOR gate. Okay, you can refer this table. This is the table same we are using here, means the function will be same. Here we are using NOR gate, so the function will be same. Simple changes, we are applying this inputs. We are added this extra AND gate. It's fine. So now we'll see the applications of the SR flip-flop. Generally, this flip-flops simply this SR flip-flop we are using switch as a switch debounce circuit. The SR flip-flops are used to eliminate mechanical bounce of the switches in digital circuits. Okay, friends, thank you.